What's up, guys? Taking a look at chapter 12 for IB Math AAHL. This is our first chapter taking a look at vectors. We're going to talk about what they are, how to do some operations with them, how to represent them, lots of other kinds of things. As you see, we have a lot of sections to get through. For the most part, generally speaking, these concepts are not so bad. Just kind of laying the framework for what vectors are. And when we get to the next couple chapters, we're going to be looking at some more challenging problems here. But let's get into it here. Let's think about vectors and how they might be used in a couple of different scenarios. So this one says an airplane in calm conditions is flying at 800 kilometers per hour due east. A cold wind suddenly blows from the southwest at 35 kilometers per hour, pushing the airplane slightly off course. All right, obviously these are things that really happen in the real world. Right now we have computer systems that help us deal with them, but in general, it's important for us to think about how greatly these things affect things like airplanes or other moving objects that we'll be discussing as well. So how can we illustrate the plane's movement and the wind using a scale diagram? Well, if we have a grid and we assign that each square in the grid represents a particular amount of, in this case, kilometers, then we can go ahead and make that scale diagram. And when we do that, the scale diagram would show you that 800 kilometers per hour is much, much more impactful than that 35 kilometers per hour wind that is happening, but it would in fact happen and it would affect it slightly there. What operation do we need to perform to find the effect of the wind on the airplane? Well, we'd have to do some trigonometry in that scenario, all right? Because in this particular case, we are not dealing with something that's going to have a right triangle. It would probably involve using a law of sines, law of cosines to find the impact of the wind. Can you use a scale diagram to determine the resulting speed and direction of the airplane? Again, yes, using trigonometry we can. So let's take a look at what vectors are, what scalars are, and how we can tell the difference between them. So it says in the opening problem, the effect of the wind on the airplane is determined by both its speed and its direction. The effect would be different if it was blowing against the airplane rather than from behind it. So that's kind of like if you go out for a bike ride and you're going along pretty good, and then all of a sudden you turn around to come home and whoa, there's that wind in your face there. Obviously, that's going to really affect how much energy you have to put forth um, to make your way back home there. So the difference between this is quantities that have only magnitude are called scalars, but if quantities have magnitude and direction, we refer to them as vectors. So speed is a scalar, but velocity is a vector. Distance is a scalar, displacement is a vector. All right. Other examples of vector quantities are acceleration, displacement, as I just said, force, and momentum. So, for example, Farmer Giles needs to remove a fence post. He starts by pushing on the post sideways to loosen the ground. Giles has a choice of how hard to push the post and in which direction. Therefore, the force he applies is a vector. Now, when we go to represent these vectors here, we use what's referred to as a directed line segment or arrow. That's the notation that we put on the top of the vector. And it says the length of the arrow represents the size or magnitude of the quantity, and the arrowhead shows its direction. So if we were looking at example 1 here, it says draw a scale diagram to represent a force of 30 newtons in a northeasterly direction. As you'll see here, we have a coordinate, a coordinate plane essentially there with the north being up and east being to the right. And if we're going in the northeast, then that means we are traveling exactly 45 degrees east of north, or north of east would be the same thing here. And you'll notice that it is an arrow. It starts right here at the origin and it goes up with an arrow at the end of it. And we have a scale in this case, 1 centimeter equals 10 newtons. Depending on what screen you're looking at, that scale may not hold in this particular case. Vector notation. Okay, so if we're looking from a vector starting from the origin, that vector would be called OA, as we see right here, OA with an arrow on top of it. In the textbook, you'll often see just a bolded letter A to represent that vector, or sometimes you'll see A with this tilde underneath it there, also represents vector A. I'll generally use the notation you see first here, OA, with the vector angle, the arrow on top of it there. If we're just talking about the magnitude or the length of the vector, we refer to that with these absolute value bars here. So absolute value bars of OA just means we're just thinking about the distance that we're traveling from O to A. Okay, so if you think about absolute value kind of being a distance from zero, it kind of makes sense to use those absolute value bars in that case there. Vector AB is a vector that originates in A and terminates or ends at B. So we call that vector AB. And we also call it a displacement vector of B relative to A. So in other words, that distance and direction, while it does go from A to B, it could also go from another point, C, to another point, D. So we can also think about vectors in that point of view as well. Now, two vectors are said to be equal if they have the same magnitude and direction. They don't have to be directly on top of each other, as long as they're parallel and in the same direction, and they are equal in length. All right, those would be considered equal vectors. All right, negative vectors. Negative vectors are parallel to each other. They have the same length, but they're going in the exact opposite direction. So here we see vector A, and here's vector negative A. Same length, they're parallel to each other, but one is going in one direction, the other one is going in the absolute opposite direction there. All right. As far as notation goes, vector AB and vector BA, those are negatives of each other as well because they're starting at the one starts where the other one ends and vice versa there. All right. So let's take a look at this example here. It says we have this parallelogram PQRS, therefore we know that opposite sides are going to be parallel and congruent. And it says that PQ, that vector is referred to as A, and vector QR is referred to as B. So when it says find the vector equations for QP, well, QP is the same as vector A, it's just going in the opposite direction. So all we have to say is vector QP is negative A. Same thing with vector RQ. RQ going from R to Q is the same thing as vector B, but going in the opposite direction. So that's negative B. Vector SR. Okay, so SR doesn't look like it has much connection to any of those other vectors, but if I look at vector A over here, it's definitely going to have the same length because parallelograms have opposite sides that are congruent, and it'll also be parallel because, again, parallelograms have opposite sides that are parallel. So therefore, vector SR is also going to be the same as vector A. And finally, SP. SP is very similar to vector B, but it's in the opposite direction, so that'll be a negative B. And again, I want to point out that as you're taking these notes here, you see it as negative and then a bolded A in your notes. You can't really show bolded, so you do negative A with the arrow on top of it to show that it is, in fact, a vector in your notes there. All right, so that's it for this section. Just a quick introduction to what vectors are. For the assignment, I'd like you guys to do page 272, 1 through 3, and then again on page 272, 1 through, well, that doesn't seem to make, I'll make sure that I have that adjusted if it happens to be wrong on the assignment in Google Classroom. Hope you guys have a great day. Take care.